a sphere, a little basketball shaped thing, they'll make flat plates that do a similar thing. The fatty acid tails interact together away from the water, but in this example, you have two flat structures coming together with the fatty acid tails between them, so no water in between. This is the classic lipid bilayer structure. Why does it do this sometimes versus this? Versus this? It has to do with the chemical structure of the lipid. A simple fatty acid would do this. A more complex lipid, like the phospholipids and sphingolipids we talked about last time, where there's two hydrocarbon tails, those don't make micelles very easily. They don't, their structure isn't too compatible with that small round spherical structure. Instead, they lay flat with the two fatty acids coming off each. And so they'll just make long sheets of this sort of thing. Just natural. Just take like phosphatidylcholine and stir it up vigorously in water, you can start seeing these kinds of structures form. So water avoidance by burying the fatty acid. What about on the edges though? You got water touching the fatty acid chains there. So when these things get big enough, they're actually more stable if they close in on themselves. So this would wrap around and form a closed loop so that there's no exposure of the fatty acid chains to water. And that's where you get something akin to a cell membrane. The small ones, we just call them vesicles. So this is an example of a vesicle. You've taken a lipid bilayer. This is a monolayer, that's a monolayer. They've come together to make a bilayer. The bilayer wraps around itself to form a closed system. There'll be some water trapped inside. So this is already a lot like a cell. The outside world and an inside world, an aqueous inside world that's separated from the outside. And again, these form spontaneously with the right lipids. You get, you sonicate the solution or something, you're going to get these. And these sorts of things can be useful in terms of drug delivery. There's a lot of interest in using these sorts of things to deliver toxic drugs. If you can get them, form these in a solution with the drug in solution, the drug will be trapped in there, and then you can kind of wash off the outside solution, and you have a little capsule with the drug inside of it. A water-soluble toxic drug. Another name for those vesicles is liposomes. And the reason that the water-soluble drugs don't come out, they're trapped in there, I said. Why are they trapped in there? If you think of anything that's charged or polar that happily dissolves in water, it's in there. Is a polar thing going to be able to successfully navigate through here? Remember, charged and polar things are kind of anathema to this. The reason the structure forms is that this doesn't like to interact with polar things. So you have polar here. This non-polar core of the bilayer is an effective barrier. Ions and things like that, maybe they can squeak through sometimes, but the pathway is not easy for them. The way we think about membranes dates to the model put forward by these two guys at UC San Diego, Singer and Nicholson. They said, the proper way to think about a membrane is like this, a two-dimensional solvent into which things dissolve that are lipidy-like. And they can move around in there. It's not a static structure. It's a two-dimensional solvent for proteins. People have used this kind of nomenclature to describe the proteins that dissolve in these membrane structures. They're the peripheral ones that are attached electrostatically to the polar head groups through ionic or hydrogen bonds. And then there are the ones that are buried deeply and interact with the fatty acid chains. Those are integral membrane proteins. You see both words here. We're going to use integral and peripheral rather than extrinsic. So here is a cell that we've dissected. We've cut away part of it and pulled it up, magnified the view on the membrane, just so we can see some details. These are the lipids, of course, with the blue polar head groups, the fatty acid chains. We've got an outer monolayer, inner monolayer. Sometimes these are called leaflets, an outer and inner leaflet. And buried in this membrane, this is the plasma membrane in this case. It's the outer one. Here's some integral membrane proteins buried deeply in them, sometimes spanning from one side to the other. So you could see something like that might be useful as a gate kind of mechanism to let things in or out. Some of the integral proteins just go halfway like this guy. But the one thing all these integral membrane proteins have in common is that they have surfaces that are what? Would you guess that they're hydrophobic or hydrophilic?
Hydrophilic.
Hydrophobic.
Why wouldn't they be half and half?
A little of both. But this part in here is there specifically because that's a hydrophobic surface and it likes to interact with the hydrophobicity of the fatty acid chains. So it's a little oily here and polar out here.
Oh, you mean the surface on the inside?
Yeah,
Okay.
this-
Okay.
This is a protein, so this is definitely different from that. This protein molecule, if it's floating out here, it's going to insert itself in there because this outer surface of it, that span there, is very hydrophobic. So hydrophobic interactions anchor these integral membrane proteins. They're very difficult to remove. The only way to get them out of these membranes